This video concentrates on the heating and cooling curve for water and how to calculate out different heats for different processes with water. For example, going from solids to liquids and liquids to gases and things like that. First off, in order to understand the heating and cooling curve of water, you have to know what the three states of water are that we use in chemistry most often. That's going to be solid, liquid, and gas. And keep in mind that solids occur below 0 degrees Celsius for water. Liquids occur between 0 and 100 degrees Celsius for water. And finally, gases occur at and above 100 degrees Celsius for water. The heating and cooling curve for water is actually the same graph, and it looks kind of like this. And on the left, on the y-axis is temperature, typically in Celsius. And then on the x-axis is heat. And as we move to the right, we're adding heat, and as we're moving to the left on the graph, we are removing heat. That's why this is the heating curve and the cooling curve. So if you're moving to the right on this graph, this is the heating of water. If you're moving on the left on this graph, that is the cooling of water. So based on the information that I told you before, hopefully you understand that if this first plateau is at 0 degrees Celsius, that this area right here is solid water, and then this second plateau, you may have guessed, is at 100 degrees Celsius, which means that the second ramp here is talking about liquid water, and the last ramp is talking about steam or gas water. So the ramps all represent one phase of matter or one state of matter for water. The plateaus represent phase changes. So this first plateau is going from a solid to a liquid, which is melting of water. The second plateau is going from a liquid to a gas, which is the boiling of water or the vaporization of water. So that's on the heating side. On the cooling side, going from gas to liquid, that's condensing water. Going from liquid to solid, that is solidifying water to make ice. There are two main equations that are used with that heating and cooling curve of water, one of which you already know, and that's Q equals MCAT. This equation is used when there is no phase change. And hopefully by now you know Q is heat, M is mass, C is specific heat, and A is not a variable. It stands for a delta sign, and T stands for temperature. The second equation that you haven't seen before is Q equals moles times the heat of fusion or vaporization. And at a higher level of chemistry, a lot of times you'll see the second equation written slightly differently. You'll see it as Q equals mass times latent heat of fusion or latent heat of vaporization. The way you'll know which your teacher is using is based on the units. The units for the heat of fusion and vaporization are typically kilojoules per mole, and the units for latent heat of fusion and vaporization is typically joules or kilojoules per gram. So you'll notice that it's per mass here, whereas here it's per mole, which is why we're multiplying by moles, and why in the second equation here we're multiplying by mass. Regardless of which of these two equations you're using or your teacher has given to you, these equations are used for phase changes, like going from a solid to a liquid or a liquid to a gas. Some common words to help you know which equation to use. Words that indicate phase changes will be like melt, solidify. These words actually are pointing to using delta H of fusion. And then words like condense, vaporize, evaporate, those type of words in a word problem are pointing you towards the heat of vaporization or the latent heat of fusion or vaporization. The most common mistake for students when using the phase changes equation is accidentally using mass all the time or moles all the time. So it's important that you know which to use, whether you're using moles or mass. And that all depends on the unit of this other value here. If the unit is kilojoules per mole, you need to multiply by mole. If the unit is something per gram, you need to multiply by mass. Whereas in the no phase change equation, m is always mass. It's never going to be moles. So I would say that's probably the biggest mistake that's made by students when doing this. For every word problem you have, you should always ask yourself first, is there a phase change going on or not? Because that dictates which of the equations you're going to be using. So in this first example I've given you, it says how much energy must be absorbed by 20 grams of water to increase its temperature from 283 degrees Celsius to 303 degrees Celsius. The fact that we don't see any words like melt, solidify, vaporize, condense, evaporate tells us that there is no phase change going on. And remember, anytime there is no phase change going on, the equation that we're using is Q equals MCAT. So let's go ahead and put in the information that we know. We know that M is mass, so that's 20.0 grams. The specific heat of water is 4.184. And the change in temperature is the final temperature minus the initial temperature. The final temperature is 303 and the initial temperature is 283. So that is 20.0 degrees Celsius. So this problem is pretty simple. All you need to do is multiply these three variables together. When doing this, I'm getting 1673.6. And sig fig wise, it looks like 3 is the least number of sig figs, so we need to round this to 3 sig figs. So that's going to be 1670, and that's going to be joules. Remember, it's joules because this was grams, that was joule per gram degree Celsius, and this was degree Celsius. So degree Celsius got crossed out, grams got crossed out, which left us with joules. Okay, and this next example problem I gave you says find the heat required to vaporize 193 grams of ethanol. It says the delta heat of fusion is 5.02 kilojoules per mole. Delta heat of vaporization is 38.6 kilojoules per mole. Just the fact that we see this word vaporize tells us that there is a phase change going on. And because it gave us the delta H of heat fusion and vaporization instead of the latent heat of fusion and vaporization, it looks like the equation that we're going to be using is Q equals moles times either the heat of fusion or vaporization. For this example, it's pretty obvious that we're going to use the heat of vaporization and not the heat of fusion. But the other way that you know which one to use and when is by looking at the phase change diagram, or this heating cooling curve for water. Remember, that's solid, liquid, and gas. If you're ever on this plateau, That's the heat of fusion. If you're ever on this plateau, that's always the heat of vaporization. So now that we know the equation, we're going to need moles instead of mass. It gave us 193 grams of ethanol, but we need to convert that 193 grams of ethanol into moles. So we have 193 grams of C2H5OH, and the molar mass of ethanol is 46.08 grams per mole. C2H5OH. So it looks like we have 4.19 moles of ethanol. So that number is going to end up going up here, 4.19 moles times, we already decided we're using the heat of vaporization even though both were given to us. The heat of vaporization of ethanol is 38.6 kilojoules per mole. And we can see that the moles are going to get canceled out here. So with 3 sig figs, my final answer is 162, and the unit is going to be kilojoules as we mentioned. So there's the final answer for that problem. Alright, let's take a look at example number 3. It says how much heat is required to vaporize 23 grams of ice, and it gives us a whole bunch of other information. Let's take a look first at our phase change diagram. Remember, that's solid, liquid, gas. It looks like we're starting with ice, so we're starting somewhere on this curve, and since it doesn't tell us a temperature, we're going to assume that we are starting maybe right there, and we want to vaporize it, which means we want to go to a gas. So we're going to end up over here on that curve. And again, because it's not telling us the temperature, we're going to assume that we're going to end up on the very bottom of that curve, which means that first we're going to have to melt the ice, then we're going to have to raise its temperature, and then we're going to have to vaporize it. So if you look here, there's really 3 different things going on. We're going to call them Q1, Q2, and Q3. It looks like Q1 and Q3 are both phase changes, whereas Q2 is not a phase change. So the equation we're going to need for Q1 is going to be moles times the heat of fusion, and that's because, remember, if you're on this bottom plateau, that's always heat of fusion. Remember that the top plateau is always heat of vaporization. Then Q2 is going to be MCAT because there's no phase change going on in Q2. Q3, on the other hand, there is a phase change. That one's going to be moles times the heat of vaporization. So for 2 of these equations, we're going to need moles, and then for the second equation, Q2, we're going to need mass. So let's go ahead and put our mass of ice into moles. 23 grams of ice, and ice is just water, so we know the molar mass of water is 18.02 grams per mole, and I'm getting about 1.28 moles. I don't want to round yet because we don't want to round in the middle of these problems, so I'm actually keeping the entire number in my calculator to keep on going, but it's about 1.28. But I'm not going to round that to 2 sig figs yet because we want to keep all of our numbers and only round once in a problem. So let's go ahead and put in our information for all of these different Q's then. For Q1, we have 1.28 moles times the heat of fusion of water, which is 6.02 kilojoules per mole. And then for MCAT, here we're going to use the mass of water times the specific heat of water times the change in temperature. And you can see in Q2 we went from 0 degrees to 100, which means our change in temperature is 100 degrees. And now for Q3, we're going to have moles again, 1.28 moles times the heat of vaporization of water, which is 43.6 kilojoules per mole. Once we know the answers to all of these, then we're just going to be able to add up Q1, Q2, and Q3. But we're going to have to make sure they're all in the same units first. But that should give us the amount of heat that's required to vaporize 23 grams of ice, just like the problem is given us. Well, I was running out of room on that slide, so I went over to this next slide and did my calculations. For Q1, I hope you got something like 7.6836 with a bunch of other numbers. Remember that I did not round that to 1.28 moles. I actually kept that entire number of moles in my calculator when doing this. And the unit here for Q1 would have been kilojoules. Then for Q2, I got 9623.2, and that unit would have been joules. Then Q3, I got 55.649278 with a bunch of other numbers after it, and that unit was kilojoules. So as I was mentioning before, we have different units here. We have kilojoules for Q1, joules for Q2, and kilojoules for Q3. So we want to get them all in the same unit first before adding all of these Q's together. I think what I'm going to do is change them all into kilojoules in order to add them together. So the only one we're really going to have to change is this one. Keep in mind there are 1,000 joules in 1 kilojoule. So I need to divide that by 1,000, and I'm getting 9.6232 kilojoules. Now that all of these are in kilojoules, I can add them all up. When I add all of these up, I get 72.956078, which a bunch of other stuff, and that's in kilojoules. Because when we're adding, remember we're using the least number of places after the decimal. The least number of places after the decimal looks like 4, so I'm going to round this to 4 places after our decimal. So my final answer is going to be 72.9561 kilojoules. So that's the amount of heat that's required to vaporize 23 grams of ice.